I always forget. So let's look at this starter code again and kind of where, you know, if we were professional computer scientists and we're doing this for a production run or something like that, the code may look a little different. But what we find, and maybe you took some CS classes where the professor said global variables can really make your code confusing and all that kind of stuff. Well, that's true. That's true. And sometimes you want to minimize the number of global variables. But what's going on here with microcontroller programming, most of the time, global variables are much easier to debug than local variables. And so what's happening is you can usually guarantee that a value is sitting, the correct value is sitting in a global variable, just because of the way the compiler works with global variables compared to local variables. Local variables sometimes can even be optimized out so that they just remain in assembly code, and the value actually never gets put back to memory. So it can be a little confusing when you try to debug local variables. Now we still, of course, will use some local variables, but we're going to find that we use quite a number of global variables. The other reason we use quite a number of global variables in this class is because you've already been seeing this. We communicate, and I'm going to try to point that out in here, we communicate between two processes on this processor. We're going to consider all these interrupts. You've been working with all these timer interrupts. We have CPU timer at 0, 1, and 2. All right? Those interrupt functions are their own little thing. You can think of them as their own little function. They get run magically. We talked about, I'm going to try to get through some of that magic today. But they are, in a sense, in a different context than your while loop that's doing all the printing. And for those two things to communicate together, the best way is global variables. Okay? Maybe someone would say, nah, it's not the best way. But whatever. A very good way to communicate between those two is global variables. Okay? Maybe you've heard things like pipes and all this crazy stuff between threads and all that. We're not going to get into that. We're going to be just using global variables. So anyway, so that's why you'll see that I have you create quite a number of global variables throughout the semester. Okay? And we're going to see this week in lab, and maybe you've already played with this, there's a view in Code Composer called the expressions view. And you can just throw all your global variables to this expression view, and it actually has a refresh rate of every second. You can start a refresh rate on your Code Composer, and it'll show you the values of all these global variables every second, which is really nice when you're debugging your code. Okay? So that you can't do that with the local variables. Anyway, okay. So let's just start from the top. So all these include files, especially this one. Where is it at? F28x project.h. This includes all the code developed for you in this thing called C2000ware that TI gives to us, right? And that's where we go into that C2000ware and then into device support, then to the F28379X and all this good stuff, right? And that's where we find our examples, don't we? But not only is the example like Lab Starter and Homework Starter sitting there, a folder up from that is there's a common folder, there's an include folder, all these. This is where they put all their library functions that we're using, okay? And when we link in that H file, all that good code is given to us to use, and it gets compiled in with our source code that we write, okay? So these includes are important, and you know, many times I'll tell you, put your global variables or put your declaration of your functions at the top of your C file. Well, what I mean by that is not all the way up here, okay? It's usually a good idea to put everything under all your pound includes. Because in those pound includes, you could be declaring some types that you need to, like for example, that int32t type. That's not a standard C type. That's something that's defined in one of those include files. So if I put int32t up above standard IO up there on H, it wouldn't know what that is. Everything is linear in C. Okay? So when it's compiling, it's going one line at a time down, and if he hasn't seen it yet, it's not going to like, if it sees a type, it's not going to say, oh, that may be coming down later. All right? It's just going to say, I don't know what that type is. Okay? So just keep that in mind. So when I say the top, I'm talking about somewhere underneath the include files. Okay, good. Excellent. Pound defines. This is something in C that you can, of course, make your own pound defines. And sometimes it's nice. There is, ways to, when you create arrays, which we'll get into a little bit of arrays when we get into the filtering lab, lab 4, and possibly after that. There's a way to like assign the size of your array by using the size of function and all that kind of stuff. But personally, that gets pretty confusing. So I personally like the idea of making a pound define size of array, okay? And a pound define, all it is just to make a way to make your code read a little bit nicer. Whenever, for example, when we put somewhere below, if we put in capital P, capital I, what the compiler does is it sees that and it replaces capital P, capital I with what's on the right side. Okay? Notice how there's not a semicolon at the end of pi there, right? And so that sometimes is confusing, and sometimes people put semicolons there, but pound define size of array, right? Or whatever, we could do something like this. Now, they do not have to be all caps. We can make it 40 long or something like that. They do not have to be all caps, but that's kind of a standard. Most programmers, when they work in C, the all cap things are usually the pound defines. So it's a good idea to not make your variables all capital letters. You can, there's nothing wrong with that, but a person looking at your code is usually going to think of all capital things as pound defines. Okay? You can put a bunch of capitals in there, but just, if you do all caps, that's usually reserved. It's not, but most programmers reserve that for pound defines. Okay? Just another way to make your code read a little bit easier. Yeah?
I was just wondering what the difference between a pound define is versus like just declaring a variable.
Sure. Sure. So, like, for example, that's a good question. So we could also do this, couldn't we? We could say int 16t. Now, an int is also, I'm just trying to get you in the habit, an int is also an int 16t. But it's a little, you may not remember that an int is an int 16t. So I want you, when you're working with ints, I really want you to use int 32t, or you can do unsigned int 16t and unsigned int 32t. Yeah, obviously, an unsigned can't go negative, but it can go positive twice as much, can't it? So an unsigned int can go up to 65,535. That's 2 to the 16th minus 1. Okay? A signed int 16t can go half that, up to 32,768, 767, I think it is, down to minus 32,768. Okay? So that's an unsigned int. So you have to think about it. Is my integer ever going to get greater than 32,000 or something like that, right? But let's say you do that, and you have a good point. What if we just did this? Array size equals 40, right? What's illegal is doing the following. This is a variable. You cannot say int 16 under t my array square bracket array size, the variable. That's illegal. Okay? But a pound define is definitely legal because all it's doing is putting 40 in there, right? It's substituting the size of array, right? That is legal. So that's one of the big things that it's used for, right? To do those kind of assignments. Good. All right, excellent. So that's exactly what I want. As you have questions as I'm going through, stop me. Stop me. This is how we get these answered. Okay. Yeah.
So if you cannot assign, so when do you use the end 32t or 16t?
Right. So one place you definitely use it, let's say you're going to count, we're going to be doing a lot of things every millisecond in this class, in our code. Sometimes we're even going to do things every 10th of a millisecond when we're sampling the audio signals and all that kind of stuff. Just imagine if you're incrementing by 1 an integer every time in that every 1 millisecond function, right? How long will it take that int 16 to count up to 32,000? Only 32 seconds, right? Because every 1,000 counts is a second. So your integer is only valid for the first 32 seconds that you run that code. It's going to roll over. So that counter keeps on counting up to 16, counts up to 32,000, then 32,700, finally to its biggest number, 32,767. Do that for me. You can take 2 to the 15th minus 1. That's 32,767. The biggest number it can be. There you get. Are you staying with me? Okay. What happens when you add 1 to 32,767? There's no higher number to go. It actually rolls down to negative, the most negative number, and then starts counting up from that. And that'll screw up your if statements, won't it, if it rolls over to negative. So, for a variable like that, or let's just say you have an integer and you want to multiply 20 times 2,000. What's that equal? That equals 40,000. That's bigger than 32,000 whatever, and so that math won't work. It'll give you the wrong number. So in that case, you got to use a 32-bit integer. That 32-bit integer can get up to, the signed integer can get up to 2 to the 31st power minus 1, which is like 2 billion something. Okay? If you figure that out, even if you count every millisecond, that is days that counter will work for. Your robot's battery will not work for days. And I definitely don't want you to have your robot powered on for days up in the lab. Okay? So that's going to work for us. Now, if we had a robot out in the world, we'd have to think about that. What do we do with that count? We would have to put some checks in there and roll it over ourselves and make sure the code can handle that and all that stuff. But here in this class, we don't have to worry about that because we're not going to have the robot on for days. Did that answer your question? Okay, so good. Excellent. All right. Let's see. Good. So pre-definitions, right? Again, the C compiler needs to know what your functions are before it calls those functions. And so you usually, it'll get pretty messy if you put all your function declarations at the top of main. It's sometimes nice to put them down below in your file, kind of out of the way once you're done with them type of thing. Once you've debugged them and you know they're working, just leave them down below. So you put pre-definitions up above so that the C compiler knows what's being passed to the function and all this good stuff. Okay? So if you ever see a little yellow ticky, so if you call a function, let's do it here. Let's see if I can compile without getting an error. Oh boy. So the word implicitly declared, you should know this error and fix it. Let's see here. Yeah, good, thanks. I mean, we can compile. But let's say we make let's do this. Let's just put this serial RXA, let's comment this out for a second. Oh, what am I doing? Trying to be fast here. All right, if I do this and I compile, Control, Save, and Build. So you should remember this one. Implicitly declared. Yep. Oh, we even got errors. Okay, let's see. Yeah, this isn't an error. A warning, it's an error. Okay, that didn't work right. Let's just make my own function. How about that? So I'm going to make a function down here. Float. What am I returning? A float in this case. Dan's function. Whatever it is. And I'm going to pass to it a float value and an int 16t. I don't know. Index. Who knows? Whatever this function is, right? And then I'm just going to say return 3.5445, whatever. Very simple function. All right, right? whatever. So I'm just going to do that. And then I'm going to call that function here before I've defined it. So let's say test equals Dan's function. Okay, and I declare. Now, test, it has to be declared anywhere outside of any function. It's a global variable. I could make it local, I guess. Yeah, but for globals, what I recommend you do is put all your globals in one spot. Where I have, right here, I have some global variables. It's a good idea, just put the rest of yours right there. So float test equals 0, just start out. Why am I assigning all these? See, the C compiler does not initialize your variables. Most of the time they are 0, but not normally. There is no initial. The only way you get your global variables initialized is if you assign them to something. If I would have just put float test semicolon, the value that the test starts out at could be anything. Okay, you got to know that. So that's why whenever you declare a variable, it's usually a good idea to give it a value. And if you don't know what value to give it 0. All right, let's see if this builds to show you that implicitly. Oh, I got to put my function back.
You didn't pass any parameters to your function.
I didn't. Oh, okay, yeah, good. Thanks. All right, where is that call that I did? Oh, up here. That's I uncommented it right here. Good. Yes, let's call Control F test. There we go, and we will pass it a float 3.1 and an integer 4. How about that? Control save. Now do it one more time. Close and build. So we do want to look at these warnings. So they're warnings over here. They're almost like errors. We got to be careful. So watch when these warnings pop up, and then it shows you the warning, and see here it says Dan's function implicitly declared. That means yes, Dan's function is declared below, but this compiler saw it before it saw its declaration. So you got to put a predefinition up at the top, all right, before it. And so that, or a lot of people, what they do is put their predefinitions in an include file, which towards the end of the semester, if you want to do that, you can do that. But for now, as I'm grading your code, I like to have it all in one file so I can see it. So I have to put a predefinition up here and just simply do that, okay? And now that it knows that, I can save, I can build, and I don't get those warnings anymore, okay? All right, I know it's an extra little annoying step, but that's just the way C programming is, okay? That's what they need. All right, good. Let's see. All right, so we got our predefinitions. Global variables, right? And then we get into main. Now, it is true, and maybe in your C++ course, if you had one, or another programming class, most of your code stayed in the main function, especially in all the C essentials, right? Everything in that, I think, in that C essentials exercise was all in main. And if main ever exits, your program's done, okay? It goes into a spin loop when you exit on a microcontroller, right? You know, a microcontroller being done is kind of, you know, interesting. I guess you just don't run any code is what done means. It's not like it comes back to your Windows screen and, you know, your program's done, right? You see the difference? Anyway, so main, of course, is an important function. C, when it compiles, knows to start your code at main. And so that's why when you hit bug, right, and you download your code, what happens? There's a little green arrow right underneath main, isn't it? So that's where your code starts, and you run, okay? And then what all this code is that we've kind of not gotten into too much is all these initializations. So we're initializing the general purpose I/O pins, the things that we used for turning on and off LEDs and reading in switches, right? Now those I/O pins can be used for other things. You're going to find when we get to the serial port lab and homework, we're going to be using some I/O pins to not turn on an LED, but to select a chip out there that we want to talk to. We have an IMU, inertial measurement unit, that gives us rate gyros and accelerations and all this great stuff. When we want to go talk to that, just like turning off an LED, we've got to pull an I/O line low. And when that chip select line is low, we can go talk to that chip. It's like select, well it is, chip select. It's selecting that chip. It's saying, hey, I want to talk to you. So I/O pins can be used for other things than just LEDs is all I'm getting at there. What this does is an I/O pin can be either an input or an output. Okay? On power up, every I/O pin defaults to an input. Okay? So if we want to drive an LED, we've got to tell those pins to be outputs. All right? And so that's exactly what all this code is doing here. This is your, I believe, your homework starter. Is that true? Let's see how many LEDs are here. Yes. So we have 16 LEDs on the homework board. You're going to find in lab, we only have 5 LEDs on the lab board. Okay, so that'll help you differentiate. But anyway, all these LEDs, and you kind of found that, you did find this in your homework, that we can talk to all these different I/O pins, right? 130, 25, 26, connected to all the different LEDs. And all I'm doing here, we're going to get to this MUX. We probably won't get to the MUX today, but for now, right now we're just thinking of all the I/O pins being input or outputs, not being a serial port. That's what we're going to talk about later, not being a PWM. And we'll explain how you get that. But you have to just say, okay, I want this to be an I/O pin. That's what this is saying. This right here, set pin options, what do you want it to be? You want it to be an output, and with what's called push-pull. Push-pull means it's actively driving the pin low, actively driving the pin high. The other way you could do outputs is with what's called an open coupler output, open collector output, excuse me, open collector output, and it generally wants it to go high and then generally wants it to go low type of thing. It's a little different. It can draw a little more current there with that other method. Anyway, so we like the push-pull. We want to drive it low, drive it high. Okay? And we're setting up all those I/O pins right there. Okay? I could have encapsulated this, into one function call, but I like you seeing all this because you're going to have to modify these. Like later on, some of these I/O pins, we're not going to want them to be driving the LEDs. We're going to be wanting them to do other things. So that's why, and it gets a little long, I get it. Now there is a way, I should figure this out. Some student found this last semester. There's a way to section off your code and put a little plus right here, and then it minimizes all that code, right? You can see that in some compilers and editors. I'll maybe look into that. They figured it out. There's a way to do that in Eclipse to make it a little easier to, not have to comb through all the code every time.
I believe you just have to encapsulate your thing with braces.
Braces, and then maybe it'll have it. Let's see, does that work for functions? Let's see. I think he had to enable something though. See, it's not there right now. You have to enable something in Eclipse for that to happen. And what Marius, right? Yes. Marius just said, when we figure that out, all you have to do, you can always do this. You can always, in C, you can put an open squirrely and a closed squirrely, and in a sense, it'll assume this is kind of like a little local function right here. And you could actually declare local variables inside there and all the kind of weird things. I don't recommend you do that. And what he was saying is there would be a little plus sign here, and you hit the plus or minus, and it'll condense all that into one line. So you don't have to scroll through all that. But anyway, sometimes that gets confusing though too. So you'll have to see if you like that mode. Anyway, okay. Good. So that's the initializations of all those GPIO pins. Here's the push buttons. See, they're being set up as inputs right here. Okay? With a pull-up resistor enabled. Remember why we needed that pull-up, right? Because when the pin isn't connected to anything, it moves high, it generally is high. So that when we're connected to those push buttons, when you push that push button, it'll pull the line low, won't it? Okay. Then we get, and that's what I hope I get to here, because these are all good questions, so we'll see how far we get. But we then have to set up all these things called the interrupts. Okay? And by the way, you folks that are coming in here late, the homework's due right at 9 a.m. So you better get your butt down here and turn it in if you're coming in here late, okay, with your homeworks. Okay. So enabling all these interrupts and this thing called the Pi That's what stands for peripheral interrupt expansion, is what PI stands for. The vector table. This is really important. This will kind of get around what I'm calling the magic of having your interrupt routines called. So we'll get to that. Okay. And so we'll talk about that today. And then what you guys have been playing with, setting up the CPU timers, right? If you ever want to, for some reason, maybe you don't want 3 timers running, the best way to disable one of those timers if you want is not to comment out this configure CPU timer function, but instead to not enable the timer. So you could comment out this, and then CPU 2 will not run if for some reason you want that. Okay. There's, take advantage of all these timers. It's kind of nice. I've had many microcontrollers in my past usage. It only has 1 timer. It's just kind of nice that you got multiple ways to do some things. Okay. Initializing the serial port. This is the serial port that communicates to TeraTerm, right? So this is how you're getting your messages to TeraTerm. Whenever you want to print to TeraTerm, you print to serial A. There's 4 serial ports on this board, and serial B, serial C, and serial D. Okay, very good. And then a little bit more with the interrupts, okay? I like to do this as the last step because we're about ready to enable the interrupts. What happens is if you enable these too soon, an interrupt can be generated while you're still in main, and then you've got to make sure to clear that interrupt source and all that kind of stuff. So we do some of the interrupt initialization up above, but then we do the final enabling of those interrupts in this little section, and then we enable what's called the global interrupt enable bit, this EINT, okay, enable int, interrupt. Until that is issued, until that command right there is issued, the only C code that can run is your main function. No interrupts can interrupt main during that time. And that's what we want when we're initializing everything. Makes sense, right? It's not until everything's initialized do we want the whole structure of our program running. Okay? So it's really important. And the good news is that all this initialization code takes no time. You're done with it real fast. Microsecond, hundreds of microseconds or something. Who knows? But really fast. Sometimes with initializations, you need to initialize stuff and delay for a little bit, like to allow the peripheral to kind of get ready. So you put a little delay in there and then continue on. So sometimes it takes a little longer. But anyway, going pretty fast. Then we enable interrupts. And then where does the C code sit? It sits inside this while loop. Okay? And we put while 1 there. That means always true, doesn't it? We stick inside that while loop and never leave. As I said again, if we would ever exit out of main, our C code, our code would be done in a sense. Now, I think interrupts could still happen if we hadn't disabled it. I don't know. Anyway, you don't want to really exit main. Okay? So we sit inside this while loop. Now, if we didn't have this thing called interrupts, that wouldn't do much, would it? I mean, well, look, in this side of this while loop, are we ever setting UART print to 1 here? No. So this code would loop and do absolutely nothing. Okay? So somehow these interrupt functions that we have down here below get called. Okay? How do they get called? Well, let's come back to that. Let's look at those functions real quick. So we're given, and you've looked at a lot of these. We're going to get to this probably lab 6, this software interrupt. We're not going to talk about this one right now. But in real short, it's an interrupt that can be uninterrupted by other interrupts. So it allows you to put a little more code in that function than you would in a normal interrupt. We'll come back to that. So it's a special thing that I'm calling a software interrupt. But what we have here, all these other interrupt functions, the timer 0, timer 1, timer 2, those are all interrupt functions. And then this guy, you saw this one, this is also kind of an interrupt function. It's a callback. It's a callback. Remember what happened? When is that called? Do you guys remember? When serial A what? Receives a character. One 8-bit character. Every time you get 8 bits, now if you're typing really fast, it keeps on sending 8 bits, doesn't it? But that gets called every time you type a character. It'll collect all those. And so that's done with the serial A's receive interrupt. Okay? We've kind of hidden a little bit of that serial interrupt. Notice a little difference that serial RXA doesn't have the type interrupt on the left side where these do. And I'll explain what that means. But what's happening is this serial RXA is being called by serial A's receive interrupt that I gave you that code anyway. So that's what's going on there. Yeah, what did you have?
So for the while one loop, if this is true, why do we need it instead of just having the if statement, just without it?
Okay, so if we're up there, if we just had if, right? Let's think about what would happen. You want to say if UARTPRINT equals 1? Is that what your if? Without the while, you're saying?
Yeah.
Okay. So without the while, well, we'd come in here. UARTPRINT, is it equal to 1? No, right? Let's say your timer hasn't happened yet, right? You just enabled interrupts, right? And you set up up here that these CPU timers, one's going to happen at 10 milliseconds, one's going to happen every 20 milliseconds, one's going to happen every 40 milliseconds, all these. So you enable interrupts right here. And I guess up here is kind of the amount of time from when you enabled the CPU timer right here. That starts the count. So when 10 milliseconds go by from this point when you started it, and then, of course, you have to enable the interrupt, the CPU timer function will be called. Okay? So initially, the first while loop, when you come in here, this first if, UARTPRINT is equal to 0. So it won't be true, and you'll come down here and you'll exit main. Agreed? If by chance, somehow it took 10 milliseconds, and UARTPRINT happened to be 1, that'd be fine. It would print once and then exit out of main, never print again. So you got to stay in there. Okay? All right. We're going to call this while loop our low priority code. Our code that takes longer to run. And why do we need it up there? Because we want it interruptible. If the code is taking a long time, that'll cause a large gap of latency in our interrupt functions, and our interrupt functions won't be called as consistently as we want. So we put our, when we get to the FFT in lab 4, we're going to show you how to run the FFT function. We're going to call the FFT function inside the while loop because it takes some time. It takes I think it's like a half of a millisecond to run the FFT, which doesn't sound like a lot, but to our processor that is a long time, right? Anyway, we'll get to that when we get to FFT. But anyway, okay, so great, we're in this while loop. Now, again, by magic, we've figured out that these interrupt functions are being called at these rates, 10 milliseconds, 20, and 40. So when 10 milliseconds happens to time out, this code is sitting here while looping. Is it equal to 1? Nope. Is it equal to 1? Nope, 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 nope. Just constantly looping here, right? Then when 10 milliseconds occurs, the CPU knows how to halt the while loop, in a sense, freeze it, interrupt it, right? And jump to your interrupt function, run the code in the interrupt function. When it's done, you exit out of the interrupt function. It just does, right? Because you get to the end. And then the CPU knows to jump back to your while loop and continue on like nothing ever interrupted it. The while loop doesn't really even know it was interrupted. The only way it knows is that maybe your function set UARTPRINT to 1, the global variable UARTPRINT. And if that happened, hey, I get to print, right? I get to end that if statement. And that's how you can periodically tell this guy to print. Printf is quite a beast of a function. It doesn't take a huge amount of time to run, but it also is not deterministic. Depending on how many float variables you pass to it and all that, it's not a deterministic function. So the larger characters you print, the longer that function takes. So that's why I put it in my not important section of code. Okay? Meaning, yes, we want it to run, but if it doesn't run immediately at 100 milliseconds, who cares, right? It's being printed to your eyes, isn't it? It's for you to see. You can't see the difference between 100 microseconds and 200 microseconds, can you? Right? So that's the low priority code. Okay. Well, yeah, we're not going to get to PWM. We'll have to do that on. Oh, okay. Yeah. So let's go and think about this now. So how does this magic happen? Right here. So what's going on inside our CPU? Remember, we have this processing unit called the arithmetic logic unit. The way opcodes in your CPU work, right? It's all linear. We do this instruction, then this, then this, then this, right? And if we have a branch, we branch to here and do it again if we're while looping or whatever, right? And everything's controlled where you're at in your code with a thing called the PC, the program counter. It's telling you where in memory you are in your program, okay? And so inside here, remember there's also memory inside the processor, our F28379D. And now dual, right, there's two of these ALUs, right? There's two cores. We're only talking about one core. Well, your program is either sitting in RAM or flash. Let's just think of it in RAM right now. And, you know, all your instructions are just one right after the other sitting in RAM. And the program counter is another register. So it's a register down here, the PC. And it just has the address of what it's pointing to sitting in it. And it changes after each instruction. So it knows to march to the next and the next. If there's a branch, it moves the PC counter to that branch location in memory, right? To do loops, to do ifs, or whatever. Okay? Now, what happens is to get these interrupts going, there is another little section in memory or flash, whatever you want to call it, called the interrupt vector table. Okay, now this is all the order and the organization of this vector table is thought of and created ahead of time by TI and the designers of this processor. All processors have this vector table for their interrupts in some fashion. Now, look at here, and we'll be looking at this come Lab 3. Let's see here. I want to show you. Oh, that's right. I don't have. Oh, shucks. I can't pull it up. Yeah, I don't have Lab 3 up here. Okay, so let's see. Oh, I do have it there, though. Concurrent library handouts. Did I put it here? Of course I didn't. Lovely. Okay, I can pull it up quick. So if I go to my PC website, come on. What's going to be the easiest way here? Create Lab 4. Let's see here. Ha! Long way here. Okay. I want all of this to just get to this table. So this table is published in the datasheet and user's guide of the processor. And let's try to zoom in here a little bit. There we go. So here is all our interrupt sources. Okay? And I only give one page here. Yeah. So here is the order of all the interrupts on the vector table. You can kind of think of this. So we have an ADC interrupt, and then it's the B interrupt for the ADC, and C, and all sorts of things. So there's all these different, the interrupt we're interested in is timer 0, this right here. Int 7, it's actually 1.7, timer 0. This is one of our interrupts that we're using with those timers. So timer interrupt 0 is 1, 2, 3, 4, 5, 6, 7 spots down on the interrupt vector table. Okay, so if I go back to my drawing here, this interrupt vector table, 1, 2, 0, 1, 2, 3, 4, 6, 7, whatever. Okay, finally, this right here, what you have to do at this location is put the name of the function, or actually the address of where the function is located in RAM. That is your interrupt function, which we called here. We called it right here, right? We said our timer 0 function is CPU timer 0 ISR. If we go look, right, we did this assignment. Look right here. This is our interrupt vector table. And notice here, we're assigning that element, timer 0's interrupt, that happens to be the 7th spot on that interrupt vector table. We're setting it equal to the address. That's what ampersand means here. The address of CPU timer 0's function name, or its function, where it's located in RAM. So by doing this, and by setting up the timer, all right, we set up the timer, we set up what happens when the timer gets an interrupt. It calls that function by setting up the vector table. And finally, by enabling interrupt number 1, we're going through this a bunch in lab 4, so don't worry too much about getting all these details. And then also right here, enabling timer interrupt 0, which was 1.7, doing all those steps now allow CPU timer 0's function to be called at the rate we specify. Okay? So, in kind of a little bit of a hand waving back at this picture here, where'd it go? Right here. We're marching along. Let's say this is our while loop in assembly code, of course, right? And we're just looping here back and forth. And it happened down here in memory is our CPU timer 0 function in RAM, right? And wherever that's located, some crazy number, right? Because it's just a list of all the RAM. Program counter is jumping down, 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 loop up, down, 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 right? Just sitting here looping, isn't it? And when 10,000 microseconds or 10 milliseconds occurs, it just happens, you know, that amount of time happens, doesn't it? When that happens, what happens is the program counter knows to jump to the correct place on the vector table. And that memory location, in a sense, gets put into the PC, into the program counter, and then it automatically jumps the code down here and runs CPU timer 0. Okay, that's great. That's how that function gets called, but there's a little more detail to this. Because what if we are in the middle of printing something? That could happen, right? You're in the middle of, maybe you got set to 1 by another timer interrupt, right? And we actually, oh, it is 1, and we start serial printf function that's taking all the floating point number that was 10.654, whatever, and says, okay, I got to print a 1, and then figure, oh, I got to print a 0, oh, I got to print a decimal place, right? It's doing all that thinking in there, right? That serial printf. What if a timer happens and we halt right there? We just put point, right, into our array of characters that we want to print out, but we still have some more decimal places to do yet. But boom, we get interrupted right there. Well, we get interrupted and we jump to the timer function. What we have to be careful. It's a special function, because what happens is you have all these registers inside the ALU that we're adding things together and deciding what the character was and all this good stuff. We have to do what's called save the context, save the state of the CPU. And so when you define a function as interrupt, like we did here, down here, some extra special things happen. If you didn't define this function as type interrupt, your code would not work. Okay? So what has to happen is when you first come to this function, the C compiler does this for us. It takes the state of the CPU and copies it all up to what's called the stack. There's an array of data that the C compiler takes for itself out of the RAM, and it's called the stack. So it takes that state of the CPU, puts it up to the stack. Then the interrupt function can just go and do whatever it wants. Use all those registers that were being used by the serial printf function and just do its own thing. And then at the end, again, because we called it of type interrupt, the C compiler knows, okay, and it's actually a different assembler instruction for returning, and it's an interrupt return assembly instruction, and that knows then to go get the data off of the stack, put it back into all the ALU registers, and then jump back to where you were in the code, and see, in that way, the while loop knows nothing happened. Does that make sense? So you halt it, you put it, save where you've been, go run your own code, do whatever you want over there, and then when you're done, everything's restored for the while loop, and it can go back to doing its thing, checking the serial port or whatever, right? What do you think about that? So that's what's going on with this thing called a hardware interrupt. Okay? And there'll be more of these, not just something that happens with time. We already see what happens when we get a character from the serial port, right? That can cause an interrupt. We can get interrupts when the ADC is done converting, the analog to digital converter, okay? Which samples an analog voltage. We'll be talking about that soon. Okay? And all sorts of things. We can get an interrupt when a ping comes back. An I/O line goes from high to low. That's called an external interrupt. We can get those. And we saw that table, there's a load of other ones there. And it's our way of scheduling other code to run. Now the other thing, I'm about done here, the other thing to know is right now, there's kind of a priority in the interrupts where, you know, like the highest interrupt will, if two happen at the same time, then the one with the higher priority runs. But only one interrupt can be running at a time. Another interrupt cannot interrupt another one unless you write some special code, like I showed you with that software interrupt. So we're just going to always, what do we just need to do then? We need to make sure then that our code runs pretty fast. Now for you, you will not be able to write enough code to make it slow unless you start doing huge for loops over all your data and all this kind of stuff. So if you write 1,000 lines of code, that's still not too slow, is what I'm trying to get at. So don't worry about, oh, I wrote too much code in this interrupt routine. This processor's plenty fast, and you don't have to worry about that.